Okay, so this is our lecture for Monday the 22nd. One thing that I've done, I forget if I mentioned it last time or not, but um, because math is a general education course, and at the college we're trying to get better about really focusing on what general education means in our gen ed disciplines. One thing that I've been trying to do is to bring in kind of a quote of the day or something into my math courses to really just focus on this idea that, rather than say like program specific courses like an accounting course or an engineering course, math is intended to be a gen ed course. Admittedly, it's a little more program specific at say the calc level, but still kind of meant to be a little more general than a very specific course. And so I've been trying to bring in, say, like a quote of the day or an idea of the day that I think applies to the course, but also to broader academics and maybe even life more broadly. So we'll talk quickly about a quote of the day. I might do one like every other day or something just because of our shortened lectures in this class. I haven't really decided that yet for the hybrid modality. The plan for today is to review 6.1. So you should have reviewed chapter 5 already. So some of that material from Calculus 1 going up through the basics of integration. And then Calculus 1 typically does cover areas between curves as kind of an application of integration. So we'll review that and then move on to finding volumes by the so-called disk, or sometimes called the washer method. Note that there are some new homeworks posted. So I posted the kind of rest of the review homeworks from chapter 5, 5.4, and 5.5, as well as 6.1. Those are due this coming Sunday. And the homeworks for the new material for this week, 6.2 and 6.3, due 2 Sundays from now. So again, the structure of the course being a hybrid course, we'll have our 2 1-hour lectures per week, and then the supplemental, something in the ballpark of an hour, 20 minutes or so, will be a supplemental recording that I'll record and post to YouTube. So typically what I'll do is I'll cover the material, at a more maybe basic level or something in the lectures, and then I'll cover some, more difficult examples or some more, maybe slightly offbeat examples or something, things that are less foundational in the supplemental material. I definitely recommend that you watch those videos and go through them, because those are, still important components, but we'll cover kind of the more foundational stuff. At least the plan most of the time will be to cover the more foundational stuff in the lectures, and then some of the more nuanced stuff, leave that to the supplement. And if you have questions about how that works or anything, take a look at, the syllabus and that workflow document to get a little more information on that. And when I post that, it'll be on YouTube. So I'll generally post those recordings to YouTube, and I'll post the link to that YouTube playlist and all of that, so you can access that video. That'll be later this week. So, probably after Thursday's class is when I'll make that recording. Okay, so the quote of the day today, in short, it's from P.T. Barnum, the famous circus guy. True economy consists in always making the income exceed the outgo. And we always prefer a margin in favor of the income. And, obviously he's kind of speaking, I think, more in economic or financial terms, but I think this general idea is really a really important life lesson in all aspects of life. Personally, I find that, like, when I'm driving or something and I leave myself just enough time to get to my destination, I tend to be more frustrated with people around me, tend to drive more aggressively, be much more, stressed out. If I leave 5 minutes early, a lot of that hassle just goes away. So, doing your best to build margin into your life, not just financially, which I know can be especially challenging as a student and all of that, but really in a lot of aspects. An exam is coming up, or you have a term paper coming up, or a project or a big lab assignment or lab report due. If you wait until 6 hours before it's due to start something you think is going to take 6 hours, you leave yourself no margin. If something happens, something comes up, that's either going to be late or it's not going to be done well. If you started a week ahead of time, something comes up that what would have become a catastrophe is merely an inconvenience. So building margin into your life, that's something that I constantly struggle with. I don't do it as much as I like, but when I do it, I typically find that my stress level goes down, my ability to handle unexpected things that comes up is much better, and my performance is much better. So something to kind of think about. I know when I was a student, I didn't do this, and maybe you'll just ignore it, but if you can be a little more organized and start, say studying for midterms or working on term papers, earlier than you even think that is an early start. If you say, oh, well, I might want to start early, go even a little before that. And hey, if you have the thing done 3 days in advance, well, that's better than having it done, hypothetically 3 days too late. Okay, so super quick review of some basics of integration. So recall that the integral a to b f of x dx represents the signed area, positive or negative, between the curve y equals f of x and the x-axis between x equals a and x equals b. So if I have a function like this between a and b, this area here is what's represented by integral a to b f of x dx. Because this area is above the x-axis, it would come in with a positive sign. But note that if I had an area below the x-axis, that gets a negative sign. Or if I have a curve that, crosses the axis, we have a positive area here, a negative area here. If I integrate from a to b, the magnitudes, it looks like, are about equal, but the signs are opposite. This total area is going to be about 0. That upper area, the positive signed area, and the negative, the lower area, the negatively signed area, will kind of like cancel each other out in terms of the integral, right? Integral 0 to 2 pi of, say, sine x dx is 0. If I have a function f of x, which is bigger than or equal to g of x on a to b, then the integral of f minus g represents the area, or we might call it the absolute area, but just kind of the area in a geometric sense, between the curves y equals f of x and y equals g of x, between x equals a and x equals b. And when I type this, I must have changed the width of my screen or something between, because I didn't, because when I was typing it, it wasn't in full screen mode. But some of my some of my my line endings and things got a little messed up. There we go. Okay, I just made this inner portion a little bit wider. That seems to have fixed it. So the area between f and g, for f bigger than g, if I'm looking to find this area, I just integrate f minus g. And I can kind of think of this as the integral of f minus g is integral of f minus integral of g, right? I'm not being super precise about anything here because, again, this, I think, should be a review. So what's the integral of f? It's this area. And then take away in the sense of like erase the area in a loose sense. Take away this area and you're left with the stuff that is under f, but not under g. These are all positive areas. If we were to look at a situation like this, just a slightly different situation, Here's our x-axis. This area here, I just want the area. I don't want a signed area. So I want this to be positive. Does G being below 0 kind of mess this up? It might seem at first glance like it could mess it up. But if I look at integral f, that comes in with a positive sign. And then minus integral G, minus integral G. But integral G, sorry, is the signed area. This area comes in with a minus sign, but it's subtracted off, which means it's kind of added to overall, which means it's globbed onto this area, right? Because the negative sign with the minus says we want to kind of add, or we want to append that area, the G area, to F. And we do see that we, up to my ability to draw artistically, which is not very good, we do see that we've recovered that same figure. So it doesn't much matter whether f and g are positive or negative if we do integral f minus g, as long as f is above g, as long as f of x is greater than or equal to g of x on a to b, we will get the kind of positive, in a sense, area between them. And of course, you could see if we moved f below 0, below the x-axis as well, for a similar reason, we'd be fine there as well. Note that if f of x is greater than or equal to 0, and if we were to choose g of x equals 0 as our kind of second function, then really we just recover this statement, right? That the integral of f of x minus 0, the integral f of x when f is positive, is just the area, because if f is positive, the sign is positive, it's just the area between the curve and x-axis. So this is kind of a generalization of this basic idea, where we're taking kind of the upper function to be f and the lower function to be g, instead of like the upper function to be f and the lower function, in a sense, to be the x-axis. And this is just kind of putting into words and mathematical symbols what I drew in pictures over here. Are there any questions on any of this so far?
No.
Yep.
I said I don't have a question.
Okay. Yeah. Sorry, I was messing with my window here. I wanted to bring up my chat, and so okay. So let's do a couple of practice problems here. So for this first problem, find the area of the region bounded by the following curves: y equals e to the x, y equals x squared minus 1, x equals -1, and x equals +1. Sorry that they're kind of like spaced funny. The Microsoft equation editor sometimes isn't too happy whenever you put in commas into your equations. Okay, so let's start with y equals e to the x. And y equals x squared minus 1. Here's maybe -1. This intercept is at 0, +1. So x squared minus 1 is x-intercepts at -1 and +1. Oh, I somehow moved that. Okay, there we go. And then x equals -1. It's this left boundary here. And x equals +1 is this right boundary. And so I see the area that I'm looking for is this area here. And I see that from x equals -1 to +1, on that whole span, the function y, the curve y equals e to the x is the upper curve, and the function or the curve y equals x squared minus 1 is the lower curve. So if I call this f and this g, then I see f is bigger than or equal to g on the domain that I'm interested in, -1 to 1. What's the area? Then is integral -1 to 1 of f minus g of e to the x minus x squared minus 1 dx. And of course, fundamental theorem of calculus, right? We just integrate term by term. We get e to the x minus x cubed over 3, and then +1 integrates to plus x from -1 to 1, right? Evaluate this at 1, subtract off evaluating this at -1. That's what this is the shorthand notation for. So this is e to the 1 minus 1 cubed over 3 plus 1. That's that part. Subtract off, evaluate this expression at -1, e to the -1, and minus 1 cubed over 3 is plus 1/3, and then -1. And I suppose we should do a little bit of cleanup on that. This is e minus 1 over e. That takes care of those. Minus 1/3 minus 1/3 is minus 2/3 plus 1 plus 1 is plus 2. And I guess we could do 2 minus 2/3 is 4/3. So, and that's our answer. Okay, so what about this next one? Find the area of the region bounded by these following curves. 4x plus y squared equals 12, and x equals y. So x equals y is a pretty easy one, but let's take a look at this. So I have a conic section here. I have x's and y's to some powers that are either 1 or 2. And so I see I have a parabola. I have one of my variables to the second power, the other variable, the highest power is the first power. If this was something like y to the first with an x to the second, I'd say that that's a parabola opening up or down. But with the y squared, this is a parabola opening left or right. Okay. So I have something like x equals, what would this be? -1/4 y squared, and then it would be plus 12 over 4 plus 3. So let me be very clear about which axis is which here, because we're not so used to parabolas opening left or right. I see that this is x equals something y squared plus something. This is a negative coefficient in front of the quadratic bit, which means we're going to be opening toward the negative side of the other variable. The negative side of x is to the left. So this should be a parabola opening to the left. Let's just kind of double check that. So if we have y equals 0, so on the x-axis, then x equals 3. And I already 3, 0. I've already got my variables backwards, but there we go. And then I see that when x is 0, when we're on the y-axis, we have y squared equals 12. So y is plus or minus root 12, or plus or minus 2 root 3. And this is my parabola. I'm actually going to redraw this top dot there. Where is my eraser? There it is. So that it looks a little more symmetric. So here's my parabola going like this. Parabola opening to the left, that's what I expected from analyzing it, and I see that plotting points, that confirms it. And then x equals y is just y equals x, my 45-degree line. So this is x equals y. This one is, what was it, 4x plus y squared equals 12. And this is the area that I'm interested in. See that there's only one finite area that is cordoned off by these two curves. Now, there's something kind of interesting about this area. I might be tempted to just do what I did before, just do something like area equals integral of something like green function minus blue function dx, and integrating from something, whatever that is on this point on the left here, to 3. And I might be tempted to just do that, but I notice that that doesn't quite work, right? That doesn't quite work because the green function is the upper bound only to the left of this intersection here between the two curves. Now to the left, integral of green to blue, green minus blue, that works fine. The green is the top function, the blue is the bottom function over that whole interval. But when I get to the right of that, whatever that x value is of that intercept there, that intersection there, well, now the green function is no longer the upper bound for my region. It's actually like the top half of the blue function is the upper bound, and the bottom half of the blue function is the lower bound. So I see a couple of things here. Number one, if I wanted to force the issue and use something like integral of green minus blue, that's only going to answer half the question. It's only going to get me the area to the left of this border. And then I have to do something else to find the area to the right. And I also see that my parabola, if I try to solve it for y in terms of x, I'm going to get a plus or minus square root of some stuff. At best, it's going to be a pretty messy thing to integrate. And I'm going to have like a, positive part and a negative part that are going to be the upper and lower bounds over here to the right. So I look at all of this, I combine all of this together, and I say, well, that seems like it's going to be a lot of hassle to do it that way. Now, sometimes with a problem, it's just a hassle, and you have to, you just have to grind through it. But for this one, does anybody have an idea of maybe a different perspective we could take, a different approach we could take that will make this a lot easier to do? Any thoughts on what I could do instead? Well, if I kind of like tilt my head 90 degrees, so to speak, to the right, if I think of x as the independent variable and y as the dependent variable, that's how I have it set up now. But if I, in a sense, kind of tilt my head to the right, or really if what I do is I flip my x and y axes about the line x equals y, if I kind of exchange the x and the y there and flip everything over that 45-degree line, then I can kind of think of y as the independent variable, x as the dependent variable. I mean, we're used to seeing x as the independent variable, y as the dependent, but is there anything wrong with talking about it the other way? Well, no, not really. In other words, could I choose to integrate by, basically setting out my Riemann boxes in this direction It really wants to make these straight lines. Just let me draw. Can I think of setting up my Riemann boxes in this direction? Treating y as the independent variable, going from this y point to this y point on my integral, and integrating dy. From this perspective, x is my dependent variable, and the quote top function from this perspective, the one that's always associated with higher values of x for a given value of y, is always the blue function. In this sense, from this perspective, the blue function is always to the right of the green function in this region. I circled the wrong piece on my axis. This is my other bound of integration at this end of this region. But I see that the blue function is always the quote top function. It's always associated with higher values of x. The green is always the quote bottom function. It's associated with lower values of x. So can I integrate blue minus green dy? This is going to be much easier. Number one, I already have things set up in terms of where I can solve them easily for x. I can get x as a function of y squared. So my f of y is going to look like a y squared. That's a lot nicer than having a bunch of square roots of things floating around. And I also don't have to break it into two integrals. Over this entire region here, I also circled the wrong upper bound. That's the upper bound. Over this entire region here, blue is always bigger than green in terms of the dependent variable x. So I can do everything in one integral, and hopefully this function will be easier to integrate than doing it the other way. Okay, so now what do the details look like? Let me try to undo all of this to get this back to something that's a little cleaner. It won't let me undo any further, but okay. So what do I want? I want to integrate from y equals a to y equals b. I'll figure out what those are in a minute. Of blue minus green. We could call this maybe f of y. In other words, x equals f of y. And we could call this maybe x equals g of y. So my area is going to be integral from y equals a to y equals b of f of y minus g of y dy. Okay, so my blue function, x equals f of y, this is just f of y. Minus my green function, g of y, x equals f of y just is y. So that's g, and this is f. We're integrating dy. And now we just have to figure out the y coordinates of these 2 points of intersection. So what do I have here? I have two equations. I want to know when those are at the same points. So I just plug x equals y into 4x plus y squared equals 12. I get, say, 4y plus y squared equals 12. Or I get y squared plus 4y minus 12 is 0. Or y plus 6. Y minus 2 is 0. Y equals 2 or negative 6. So clearly this is negative 6, and this is 2. So we just need to integrate this polynomial in y from negative 6 to 2. Super important. the variable in the integrand is y, and the variable of integration is y, and our bounds are related to the y-axis. I can shift my perspective, but I have to make sure that I maintain consistency, that I shift it in the integrand, the variable of integration, and in the bounds. Have to make sure that I've made all of those shifts correctly. Any questions on this? And integrating a polynomial, shouldn't be super challenging. So, given our limited time here, I'm gonna just kind of leave this here, and you could carry out the details and wrap it up if you want to. If you're looking for an exercise for, fundamental theorem of calculus, a little bit of practice on integration techniques and so on. Okay, so moving on to 6.2, finding volumes. Oh, sorry about that. I'm having some HVAC heating problems, and that's the furnace guy calling back, but I'll get back to him after class. Okay, so finding volumes. So first, we'll start with the definition of a volume. We'll let S be a solid that lies between x equals a and x equals b, so a three-dimensional structure. And let's suppose we have a cross-sectional area. So here's, let's say, my x-axis, and maybe I have, let's just draw a sphere. If I have a cross-sectional area in plane px that's perpendicular to the x-axis, so I'm imagining a plane like this. This plane is perpendicular to the x-axis. And I note that when I take this cross-section through the sphere, there's going to be kind of this boundary line here where the plane cuts the boundary of the sphere, and there's going to be kind of material of the sphere there, right? That's inside of that boundary. So that's what my plane PX kind of looks like. And it's taking a cross-sectional area, two-dimensional area, from this sphere. So let's pull PX out here and lay it flat. We have this boundary of the sphere where it intersects with the plane PX. And this is that kind of inner material of the sphere that we've cut through. Now we're saying this cross-sectional area, if we denote this area with A of x, so this area in here, we're going to call A of x. This is an area that's a function of x. If I move my plane kind of to the right, I have a smaller cross-section. I have a smaller area. If I moved it to the left, I have a larger area. So if we go through this process, if we figure out what A of x is, say as a function of x, and I know that my sphere goes from x equals a to x equals b, or I mean, I'm saying sphere here, but it could be a irregularly shaped object. It's just a little easier to draw and to envision what it looks like with a sphere. Then my volume is defined as the integral of the cross-sectional area. And the book has super nice pictures that kind of build all of this up. But I always think of it, I don't know if you've ever seen those like puzzles that are like 3D sculpture puzzles, where, they give you a lot of just like flat pieces, and you stack, the pieces up in a certain order, and it like makes the bust of a person or something. So you have all of these like contours, or these little tiny, wafers or discs or whatever you want to call them. And when you stack them up, it kind of builds up a 3D structure. It doesn't look perfect. It's like a little jagged at, when it comes in or goes out. But it's kind of that rough representation of that three-dimensional solid. And that's kind of what we're doing here. We're thinking of, constructing this with like Riemann boxes, or something that's a little more like maybe Riemann slices. like Riemann little cross-sectional little short cylinders that were stacking up. And as I start on the right side, I add on a really small cylinder, and then I get a cylinder of larger radius and larger radius and larger radius that I'm stacking as I get closer to the middle of the sphere closer to x equals 0. I have a really big, a large radius cylinder that's still, pretty thin that I'm adding on. And then I go back down the other side. Right. I add a lot of these wafers or discs together and I get something that looks roughly like the sphere, but it's kind of, all jaggedy. But then as I take the limit, as the thickness of my cylinders goes to 0 and the number of cylinders goes to infinity, when I kind of add up all of those infinitesimal areas infinitely many times, that's when I pass to the integral from the sum. And that's also when I pass from that kind of jaggedy approximation to the actual smooth solid. Okay, so hopefully that makes sense. And again, there are some pictures in the book that if you didn't really follow what I was saying with stacking the wafers up and all of that, you can look at the pictures in the book that might help also. So let's compute the volume of such a sphere. Okay, so what do we have? We have a 3D object. Let's start by drawing it. And this is a sphere of radius r. So it goes from negative r to positive r, and the x-axis, we'll just center it at 0. Now, one little detail, technically a sphere is the surface of this solid. So we would call it a ball if we wanted to be really specific, but I'll just refer to the solid itself as a sphere. Technically in math, we'd call that a ball, and the surface, the boundary layer, would be the sphere. Okay, so x is going from minus r to r. Our plane perpendicular to x, dx, goes like this. We have this cross-sectional area. If I pull that plane out, I have area A of x here. I'm not going to shade it this time. And I see that going around the x-axis, because of the nice symmetry of this sphere, this is going to be the same radius the whole time. This is going to be the same radius in all directions as we're going around the x-axis. In particular, let me get a different color here. The radius going from the x-axis straight up, I didn't quite match my upper point there, but going from the x-axis straight up, that's going to be the same radius as, going 45 degrees this way or going straight down or any other direction. And if I call this axis y, I just see that this is the y value associated with this particular choice of x here. The particular choice of x where my plane px is slicing through the x-axis. In other words, this radius is, we'll just call it y. So a of x then is, well, what's the area inside this circle? Pi times the square of the radius, just pi y squared. Okay, so we're almost there. We want to integrate from x equals minus r to r of the area a of x. I'll leave it like this for now, dx. I have one last problem. My variable of integration, my limits of integration are all phrased in terms of x. I have my integrand phrased in terms of y. Well, that's not too bad because I can just relate x to y. that was a little bit long of an x-axis. There we go. If I look at how x relates to y in this kind of xy plane cross section, I have the top half of a sphere here, or that's y squared plus x squared equals r squared, or y squared equals r squared minus x squared. And I'm actually not even looking for y specifically, I'm looking for y squared. So that's all I need. So this is my volume is given by this integral, the integral of the cross-sectional area A of x dx. And now I just swap in r squared minus x squared for the y squared. Now my bounds, my integrand, and my integral of my variable of integration all match. They're all x. So when I integrate, I get r squared x minus 1/3 x cubed from minus r to r. This gives me r cubed minus 1/3 r cubed. Subtract off the same thing with minus r. So when x is minus r, this gives me a minus r cubed plus 1/3 r cubed. So I have r cubed plus r cubed minus a third minus a third. That gives me 4/3 pi r cubed. And we should recognize that as the volume of a sphere with radius r. One little note here, we could have made the calculations a little simpler by recognizing at this point that I have a symmetric interval, symmetric about 0, and my integrand is an even function. So this is a nice tool to have in your back pocket, especially for Calc 2, and we're doing a lot of integrals. Integrating a symmetric function over a symmetric interval, an even function over a symmetric interval. We could just double this and integrate from 0 to b because of the evenness of the integrand and also the symmetry of the interval. If either one of those symmetries breaks, we can't use this trick. What would that do? That would put a 2 here, and that would get rid of these, and we'd have 2/3 r cubed times 2 pi, 4/3 pi r cubed, saving us just a little hassle with negative signs. And by little hassle, I mean it can be a little bigger of a hassle, because when you've got lots of negatives floating around, that's when you're really likely to make a mistake. So sometimes this can be a really nice trick to use. Any questions so far? Okay, so just a side note, we had a solid up here that was a sphere, and we just kind of attacked it directly with the definition. But if we have a solid that's not as easy to work with of a kind of geometric object, we might want to try to recognize that solid as being created or constructed by rotating a function y equals f of x about the x-axis. In other words, we could think about the sphere being constructed by rotating this curve about the x-axis. So when the kind of that loop of wire, so to speak, kind of rotates all the way around, that would cordon off a section of space inside of its whole path that would be that sphere, that volume. And in that case, then our cross-sectional area is always going to be pi y squared, where y is f of x. And our volume then is going to be integral a to b, pi y squared dx or just pi times f of x squared dx. Okay, so I think we should have time to get through at least one more of these. So let's work through this one and we might get to the last problem. Or if we don't get to it, I'll just put it in the supplement. So let's compute the volume of the solid obtained by rotating the region R about the x-axis. So we'll start by drawing the region. R is the region in the first quadrant bounded by these curves. So we have a curve x equals 2. That's the black curve here. And y squared equals 8x. So this is like x equals 1/8 y squared. This is a parabola opening to the right. We see when x equals 0, y equals 0. And when x equals 2, y squared is 16, y is 4. This is my region R. And I always like to also draw which axis I'm rotating around. If I were to take the same region and rotate it about the y-axis, I'd have a very different looking solid and a very different volume than if I rotate the same region about the x-axis. So just to keep in mind which direction I'm going, I like to indicate that on my picture also. I also like to try to keep my colors the same. Try to keep my colors consistent here. So when I rotate this around, it's going to mirror over to something like this on the other side. Oh, let me redo those curves. Yeah. So if I'm kind of looking from the perspective of being a little bit to the right of the object, my blue curve, when it wraps around, it's going to kind of make this outside here blue. And then this black curve here, when we wrap everything around, this kind of top flat surface here is going to be black. So I have something that looks like, a bowl or something that's filled in, that's, kind of pointed to the right. Okay, so in this case, what have I done? I rotated a function about the x-axis. I could go from first principles and say, I have a plane px. I have a plane px perpendicular to the x-axis. Because there's a nice circular symmetry here, I rotated the curve around the x-axis. This is always going to be a circle. It's going to be a circle, right? Same radius everywhere. Right in the middle here is the x-axis kind of poking through. It's going to be the same radius in any direction. So I can pick any radius that I know. And in particular, if I go straight up, that's going to be the y value associated with this x. I won't draw it straight up here. I'll draw it a little off to the side just to remind ourselves that this is going to be the same radius everywhere. This cross-sectional area, a of x is pi y squared. And we now see where this volume calculation comes from, this volume formula. And I see that my volume is given by integral. Now I need to figure out which X I start at and which X I end at. Where do I kind of start adding these wafers here? And where is my last wafer? I start at X equals 0 and go up to X equals 2. I can see that very clearly from my region, looking at my region. I want to integrate pi y squared. Nicely enough, we already have y squared equals 8x. And of course, we're integrating dx. Everything is consistent between the picture, my integrand, my variable of integration, and my bounds. I just want to make sure all of those mesh and that I'm not, having one variable in some places and a different variable in other places. Everything is in terms of x. So it looks good. So we have 8 pi times x squared over 2. Or this is 4 pi times 4 is 16 pi. And that's our answer. Are there any questions on this one? Okay, so working through the last example then, similar type of example, compute the volume of a solid obtained by rotating the region y about the y-axis. So we want to be careful there. Where R is this region that's given? So R is the region bounded by x equals 0. In other words, the y-axis. Y equals 3. And, well, x equals 2 root 10y. This means that x squared equals, well, that's 20 times, or sorry, 4 times 10, 40, y. So this is like y equals x squared. This is a parabola that is like opening up. So it's going to look like that. And very importantly, we're rotating about the y-axis. So we want to make sure to rotate this way. So rotating this region about the y-axis. It does take some time to draw all these pictures, but I think it's so important to draw the pictures because if you don't have the pictures to go on, you'll see if you try to like rotate about a different axis, it's not, say, a clear x or y axis. If it's something a little bit different, you really have nowhere to even start. If you always start with drawing the pictures, understanding the geometry, number one, you just kind of make sure that everything's pointing in the right direction. I think we can intuitively see here that we're going to be integrating dy, so we don't want to just grab this formula verbatim. We might need to make an adjustment. And if we understand it, if we understand the geometry, understand where all these pieces are coming from, we can make those adjustments much more easily than if we're just trying to like memorize a formula and just use that formula. We don't really understand how all the pieces are interrelating. But okay, so let's actually want to keep this at kind of the same level. So just erase that bit. So here's y equals 3. We have our green top and our blue curve. When this rotates around the y-axis, it's going to mirror over to the left side. And again, we're going to have kind of a blue outside here. There's going to be this top here like this. And then this green line at the top will have circled around and made kind of a green border at the top here. Now, when I take my plane, if I take, say, a plane PX, if I like insist on using PX for my plane, my cross-sectional area looks complicated. It's kind of like something that looks a bit like a parabola with like a flat top. You know, could I figure out what this area is in terms of X? Yeah, maybe I could. I mean, we figured out areas like this in 6-1, but it's not nearly as clean as if I chose to shift my perspective and go with PY, a plane perpendicular to Y. There we go. I wish I could like set a point and just like tell it rewind to that point, but I think that might be asking a little too much of a Microsoft product. I always have to get a dig in at Microsoft when I can. So if I use PY instead, plane perpendicular to the Y-axis, nicely enough, now my cross-sectional area is a circle, which is a little hard to see from my bad drawing there, but PY, we have a circle. For an arbitrary radius, since it's a circle, the radius is going to be the same in any direction. But I see that if I point directly out to the right, for this value of Y, that's associated with X. So I just have radius X, and I'm looking for cross-sectional area A of Y. So for a given Y, for a given height, what's my cross-sectional area? And then I stack those wafers bottom to top instead of left to right. A of Y is going to be pi x squared, right? So this is similar setup to up here, but just swapping X and Y. And we're integrating for our volume, we're integrating from Y equals something to something of pi times x squared dy. We see we're integrating from Y equals 0 to 3. And I erased it from before, but x squared is 40y. That 40y is x squared, so I've already taken care of the square. I don't want 40y all squared. I've already done the square over there. So this whole bit is x squared. Or this is 40 pi times 1/2 y squared from 0 to 3. Or this is what, 20 pi times 9. 180 pi if I did all of my ciphering correctly. Any questions on any of this?